All right. Good afternoon, everybody. First of all, I apologize for not being able to be here today. Last week was actually something I was aware of. I was trying to get you guys to take the test before. I had to leave for that week. Uh, but unfortunately, with snow days, it just kind of pushed our schedule around. And so that's why you kind of had last week just the practice problems, which I know because we're still in the process of practicing much of those problems, I know that maybe that practice didn't go perfectly. And so when I return on Thursday, I'm going to give you guys the option. If you guys want to take the test that day, you can. If if you feel ready, you certainly can. Or you can use that day for study and asking questions and just kind of working with the material. And you guys can decide that individually or as a class. It's up to you, right? Make sure you're still practicing those problems, obviously, regardless of what you're going to pick, and studying. And then, of course, this set of problems, which I know is kind of weirdly numbered because I made some cuts and didn't renumber it. Apologies again for that. Hopefully watching this video to get some of that information, just make sure you know in your head. So let's go ahead and get started. And of course, I'll try to make a series of these so they're all kind of like one question per video. Right, yeah. So first question, if the triangles here are known to be similar, and let's keep in mind that symbol right there just means that they are similar, not congruent, similar, mathematically speaking. What definition must they follow? Lists the relationship. Okay, so here's how this question is really asking. We know these triangles are similar, right? So we're being told that in the problem. Even if we weren't, we have some angles. And so this memory that I'm trying to trigger right now is actually the answer to the question. And so if we know the triangles are mathematically similar, the question is really just asking, well, what do we know about the shapes themselves? And really, it always comes down to two things. We know something about the sides, and we know something about the angles. And most specifically, from the definition from our work, we know that all corresponding angles have to be congruent, and we also know all corresponding sides have to be proportional. And keep in mind, proportionality just means the same ratio. All right, let me zoom out just a little bit here. Let's go to 125. Okay, so what am I talking about with angles congruent? Well, I mean, that's been kind of the thing about the relationship of angles really with anything we studied. Angles, if you're going to have relational shapes, have to be congruent. And so when I say make a list, this is what I'm talking about. Now, correspondence, of course, just to recall, just means they're in the same relative location in both triangles. And so these are corresponding angles because they're both located at the top. B and Q, they're located bottom right, okay, and then C and R located B and Q bottom left, C and R bottom right, okay? And so that's one half of the relationship. Now we know there's other things true, like, coordinates, scale, lines of dilation, scale, perimeter, and area all interact with the K factor, but the most basic version of this relationship is that all angles had to be congruent and all sides being proportional. Now, if we examine sides being proportional, being the same ratio, well, scaled shapes have a multiplication factor. We can take all the sides of like the small triangle, multiply it by a number larger than 1, and get all the sides of the larger triangle. Or going backwards, we can take all the large side lengths, multiply it by a number less than 1, still positive, and we'll end up reducing or shrinking the shape down, right? Now, the problem is when you're trying to like understand proportionality, it is explained through multiplication, but we don't always know what the multiplication numbers are. Like this example is a good example of that. We don't know side lengths, but we still have to somehow represent proportionality. All right, well, here's where basic algebra comes in. So if you multiply, scaling is explained by multiplication, but you don't know the multiplication, you have to work backwards. And as you know, the opposite of multiplication is division, and so that's where we have this idea of ratios. So all ratio work proportional work, is just exploiting the fact that if I have scaled shapes, and their sides can be explained by multiplication, I can really show it through division. And that's what ratios are. And so when you think about these shapes, okay, all we're looking again is like for correspondence. And so if I take the left-hand side, say, of the two triangles, those become my working ratio. In this case, AB over PQ. Now, of course, ratios can flip, right? And so you could have written it small triangle over large triangle. But the important part is, like, once you establish a ratio, you have to follow it. And so if the very first ratio in the sequence is big triangle over small triangle, they all have to be. But this would be the written ratio that would have to be true if you have correspondence here. And of course, like, it would follow that BC, let's see, BC here, as corresponding in a ratio QR. And then AC with PR, excuse me. Okay? And so this all the question was asking is like, do you understand the two main components of similarity, which is angles, all corresponding angles are congruent, and then all corresponding sides are in the same ratio, hence proportionality. And so like, can you list that after you like state that relationship, right? So that's the first question. I'll see you in the next video.